First of all, the first thing I want to do in this conference, apart from the introduction, is to announce the recipient of the Peter Barnett Memorial Award. This is a roughly annual award that the Institute of Acoustics bestows on people for their contribution in one way or another to the art. And our recipient this year is Mark Dodd from GP Acoustics, or better known as from KEF or Celestion, or both, or all of them. And I'd like to read out a citation, and I will have to put my glasses on for this. Unfortunately, I'm at this stage of life where I'm halfway between wearing glasses and not, so it's all a bit awkward. Here we go. Okay. So Mark Dodd has been working in the loudspeaker industry for over 30 years. You wouldn't know it to look at him, of course. During which time he's been responsible for a number of important advances in loudspeaker technology. Mark's work can be characterized by dedication to the application of science in the pursuit of perfection. Mark graduated with a BSc in physics from the University of Southampton, just up the road, in 1979. And started his career in audio at Vitavox in 1981. Here he had his first experience in loudspeaker compression driver design. During this time, he undertook a part-time master's degree in applied acoustics at Chelsea College, London University, and was awarded an MSc in 1986. He then joined Tannoy, where he developed the Tulip waveguide. This is a phaseplug for their coaxial drivers, on which he presented his first paper in the 1992 AES convention in Vienna. The Tulip waveguides are still used in many of Tannoy's current professional and high-end domestic loudspeakers. In 1994, Mark joined GP Acoustics, a group including KEF and Celestion, becoming head of group research in 2001. At GP Acoustics, Mark developed compression drivers for Celestion and was responsible for the concept and HF design of the KEF UniQ loudspeaker drivers, including the Tangerine waveguide, and pioneered the use of finite element analysis and transducer design. He has presented several papers on loudspeaker driver and enclosure design at AES, IOA, and ISEAT conferences. The Peter Barnett Memorial Award recognizes advancements and technical excellence in the fields of electroacoustics, speech intelligibility, and education in acoustics and electroacoustics. And, although it is mainly the first of these for which Mark would normally be associated, through his dedication to the application of state-of-the-art scientific methods, his work has had and will continue to have impact on many of these fields. I'd now like to introduce Joe Webb, who's the president of the Institute of Acoustics, who will be awarding the award to Mark. Thank you, Joe.
Right, thank you for attending Reproduce Sound. I'd like to invite Mark up now to receive the award.
Okay, well, I'd just like to thank everybody very much indeed. This award means a tremendous amount to me. I've been coming to the IOA coming on for 30 years, I think. And I have a lot of friends here and a lot of colleagues I've got very deep respect for. So to get the award here means more to me than anything else could have, actually. It's fantastic. So thank you all very much indeed. Okay, and now to work. I thought today I'd talk about some developments in wideband transducers. Actually, I'm going to talk about transducer arrays and also single transducers with point source characteristics. So I'll start off historically just to have a quick look at the dual concentric. Keith mentioned the tulip waveguide, and I'll just introduce very quickly the design that I presented in the paper in 1992 and some conclusions from it. Then I'll look at a paradigm that we've adopted to clarify exactly what we're aiming to do when we design one of these loudspeakers. I'll then go through some of the major developments in coincident source driver technology. I'm just going to look at the radiating parts. I'm not going to look at motors. I'm not going to try and do everything. So that should be reasonably brief. After which I'll look at some enclosure design examples. The blade, I'll just focus on the array configuration and diffraction. The LS50 will be a bit more in depth, and I think that'll illustrate quite well some of the techniques that I'm going to talk about. After that, we have something completely different. We'll look at a compression driver that has an Axiperiodic diaphragm. And I won't say any more about that just now. It can be a bit of a mystery for now. So back in the early days, actually before I went to university, I bought a pair of these drive units and put them in some boxes and spent many happy hours listening to them. They were, well, they still are because they're still made. It's a very characterful design, shall we say. The response is not particularly flat, and the dispersion, these are 15-degree off-axis curves. So on axis here, 15, 30, and so on. The dispersion actually drops off quite quickly as you go off-axis, and the subjective impression is very strong. It's like you have a beam of sound coming out from the front. And then as you move away, the high frequencies die away. So the new design moved away from the traditional phase plug design and slightly changed the configuration. There's now an HF diaphragm behind a phase plug that's formed from annular air channels. And the idea was to make a loudspeaker for the PA market that had much wider high-frequency dispersion, so we could cover an audience area better. The waveguide here is approximately conical, and then it's terminated onto the flat baffle with the idea that the directivity can be controlled with it. And actually, one thing worth mentioning, I did do some work on acoustic impedance, and I predicted the acoustic impedance of the driver here. Actually, I was quite lucky. I was in touch with a researcher at Southampton University, Keith Holland, and Keith also made some measurements which in the paper we compared to the simulations, and they were pretty accurate. And I think it's generally fair to say that that kind of straight axi-symmetric exponential flare is actually quite benign. You don't see the kind of ripple that you'll see in an exponential horn in the classic textbooks. In the real thing, that isn't actually a problem. And it's just really because of the proportions. So looking at the response, how well did it work? Well, we aimed to produce a spherical wave at the end of the phase plug. 15 degrees is really close. It's very good indeed. Actually, 30 degrees is pretty good as well. It's still closer than 6 dB. The actual response itself, well, this bit here, I now know that's a phase plug resonance. And we made some mistakes in the phase plug design because at that stage I really didn't understand what was going on at all. So the high frequency response then falls apart a bit. But it was a brave effort. And there were lots more tulip waveguide drive units, and those are still around. So it was a useful and interesting bit of work, that. But we got some conclusions from it when we listened to it. As I mentioned, diaphragm breakup was an issue. It was still an issue on the new drive unit. We still had a low frequency diaphragm that broke up well below the crossover point, and also a high frequency diaphragm that broke up in the audible range as well. And that's quite noticeable. The other thing was that the classic design, which has got narrow high frequency dispersion and this rising response on axis that goes up as the frequency increases, you can't balance those flat. You get a dull sound. The new design had much wider dispersion, and you could balance it so that in a normal room, a flat axial response sounds balanced. And actually, the sound quality was quite different as well. It was more spacious, and dare I say it, more natural. The other thing that happened was the soundstage moved from the kind of typical tannoy in-your-face image of the old monitors, really close sensation. It moved further back, which was actually quite a nice effect as well. So from that, I came to the conclusion that wide dispersion works really well in a domestic-sized room. And then at that stage, it was all change. So this is a good place just to look at what the paradigm we adopted really means. So we want something that's a bit like a point source, so it's not going to interfere with itself, dare I say it, this early in the morning. We want the pressure just to follow the input voltage. And to get a power response that slopes smoothly down, as we know, gives a nice sound, and an axial response, we need the right kind of dispersion. So that turns out to be dispersion that progressively narrows as the frequency increases. We also want to avoid secondary radiation. So secondary radiation really is any sound that isn't part of this main signal. And it can be caused by resonances in the diaphragm, by resonances in the enclosure walls. Diffraction is another sound source. We don't want that. Port turbulence, all sorts of mechanisms make sounds that we don't want. So this paradigm was one that really we've had and worked to, I think, probably for the last, it's almost 20 years now. And interestingly enough, it turns out that it satisfies Floyd Toole's requirements for a good loudspeaker. He's particularly keen on this falling power response. And we found that in practice, we think he's actually right about that. And that does seem to be one of the things that people actually like in a loudspeaker. It's a characteristic they like. So then I moved companies. And I moved to a company that made a different kind of driver. But in the meantime, for various reasons, I ended up working on compression drivers for a while. And I had a great opportunity to learn about finite element analysis and to use the laser Doppler interferometer scanners that Celestion had at the time, which were quite unique in the loudspeaker world at that stage. So I started to get some real high-level experience in modeling and spent several years working on that, learning different modeling techniques, and also trying to edge towards making acoustic finite element analysis into a tool we could use every day. We've been very lucky. We've always used PayFec, which is an extremely good piece of software because it couples acoustic and vibrational domains so well. But although the solver in it is tremendously capable, actually getting from a design to a model was quite difficult. So after several years of that and really making quite a bit of progress, I started working on these coincident driver arrays. So it's similar to a dual concentric. Instead of the HF unit being back here and the pole being a horn, there's a neodymium magnet, a very compact magnet, and a diaphragm at the apex of the cone. So you end up with a direct radiating coincident source. Now, I'm just going to talk a little bit about the analysis strategy at this stage because that was really what came out of the work. And it's quite important to approach using a tool like the finite element method in a constructive way. It's very easy to go off and get lost in it and end up with millions of pretty color pictures and no idea of what's happening. So one of the things that we found was really effective was rather than diving in and modeling a whole driver and trying to model the magnetic bit, the eddy currents, the nonlinear motion of the voice coil, the vibration of the diaphragm, radiation inside and outside of the box, and the enclosure vibrating, instead of looking at everything and having some kind of a God's eye view of the horrendous complexity of the real world, we try and break things down into smaller parts. We try and abstract a particular behavior in a very simple model to get a clear result of that particular aspect of behavior. So as an example for this, it just so happens that the first thing I was going to talk about in terms of driver technology fits this category really well. What I wanted to look at was the geometry of the waveguide interacting with the geometry of the diaphragm. And we use a spherical cap diaphragm, which I'll call a dome because it's a lot shorter. And we had a bit of a problem with the early designs, which you'll see in a minute, that I needed to fix. So I thought it might be something to do with this geometry. So rather than having a finite cone-shaped flare with mouth endings and diffraction, what I did was I created a model with just an infinite cone. So this part here is finite element fluid, and these are wave envelope elements that give the effect of having an infinite conical waveguide. And what the model allowed me to do was it allowed me to vary the angle of the waveguide and the angle of the dome, so to make the dome deep and then shallow. If we adjusted it to represent as closely as possible the original geometry that I started working with, we found that on axis, that's the red curve here, we had a big dip. It's actually around 17, 18 kilohertz. And that's actually there on the real drivers. Just on axis, you get a dip at high frequencies. And this was a bit of a disaster because it meant we had this coincident source array. The sound all comes from one point. Oh, but we've got a super tweeter on top, which was a bit, it was a bit of a broken paradigm there. So what I looked at was slightly, I mean, to me it's a little bit obvious, is a diaphragm that's actually perpendicular to the waveguide. So it's got the same angle as the waveguide. And then, of course, you get a much smoother response. So although I'm not providing a pulsating sphere into a conical waveguide that would give a perfect result, even though it's axial motion, if the angles are matched up, the error in amplitude of pressure is not big enough to cause a huge problem here. There's a little bit of a problem, but not so severe. And that meant that if we could harness this, we could avoid using the additional driver. But of course, as is so often the case, nothing comes free. And although an 80-degree dome is desirable from the acoustics point of view, well, necessary from the acoustics point of view, it gives about a 20 kilohertz first resonance. So that's far too low to be usable. That would actually sound completely hideous because you'd have several dB deviation around 15 kilohertz. It would be very, very audible indeed. So we had to fix that. So then came a stage of doing just some simple finite element modeling of the vibration of the dome and moving on fairly quickly to couple models where we looked at the radiation. And what I found was that if I kept a profile of a stiffener part that we have here to be more like the original dome and put the acoustically shaped dome in front, I could end up with a compound shape that actually had a quite decent 35 kilohertz resonance. And you know, that's to say, I'm not saying that I can hear 35 kilohertz, just that it's such a big peak that the sides of it need to be away from the audio bandwidth. And that seems to be a good frequency. So the other technique is, could I have a glass of water? The other technique is to do more complete models. Now, rather than resorting to fully coupled finite element models, which are really hopelessly difficult to set up and solve, and very slow as well, the approach we take is to link different solutions from different models to combine FEM and analytic models and then try and get something that we can directly compare to measured results. So the way the process worked was we'd have our FE preprocessors and CAD. And we'd draw a geometry in, say, NX, mesh it in the same software, and then using a program Patrick wrote. And this was actually the key to making PAFEC usable, was mesh to path, this little program we run in a terminal that Patrick wrote for me. I think it took him an afternoon to get the first draft, and it was about a week, wasn't it, until we actually had something that pretty well did everything. What this allowed us to do was we used material names to define what kind of elements and some of the boundary conditions. And we went from a very slow setup using this little terminal program to a very fast one. So CAD and mesh, through mesh to path, into PAFEC to do the acoustic solving, and then the results could then be taken into projector, where we could, for example, add a constant velocity drive to it or do all sorts of different things to it. We could also analyze the magnetics, and we could put, say, the BL characteristic from the magnetic software, and perhaps we might also put the blocked coil impedance from a magnetodynamic solution. So if we've got a steady state vibroacoustic solution, we can then produce SPL, impedance, and displacement. And of course, we can measure all of these relatively easily. So we can then start comparing the models to the real world. And that kind of validation is absolutely key. So the other thing is, it's not enough just to analyze. We also need to listen. And we need to listen because we always simplify the models. And quite often we throw out the baby with the bathwater. We leave out things that do actually matter. So we'd listen, we'd hear something, we'd try and isolate that by measurement. And then we'd think about where it came from and try and model it with FE. And in the FE domain, it's quick and easy to fix it. So then we'd revise the prototype and we'd measure it again and listen to it. Every single time we simplified the behavior by removing some kind of irregularity, it always sounded better. So if there is a black art in loudspeaker design, I haven't found it yet. Seems to be a lot of engineering. So the next thing was to try and make an even nicer wavefront. And I wanted to build on the work we'd already done on diaphragm and waveguide geometry. So we took a radial segment and started off with just the same geometry, but removed some of the air, which is how we think in terms of acoustics, to get a radial phase plug. And what we could do with this, we could vary the width here to avoid exciting resonances. And we could also use a deeper dome. So here's the diaphragm, and it's radiating backwards down a tube. That's the wasted sound. And this part here is the phase plug. And you can see that it generates this spherical wave that gives us nice wide dispersion. So we also had a wider angle dome, which gave a higher resonance. So we pushed the dome resonance up to about 40K. And of course, because it is effectively, it's a horn-loaded system, so we get an increase in efficiency and power handling. And of course, if there are any people here from consumer audio, it's not a horn, it's a waveguide. So another piece of work that actually was carried out by a colleague of mine, Jack Ockley-Brown, was to try and figure out how to fix this problem up here. If you have a normal roll surround, and you look at an impulse from the high frequency unit, as the wave travels down the cone and gets to the surround, you get a very clear reflected wave. So if we watch this once more, you can see bing. And then you can see on axis how big the interference is because of the symmetry. So this is causing major problems. This is one of the things that causes the big irregularities as you go on and off axis. And really, it's the main culprit for beaming. So what Jack came up with in this instance was a much flatter surround geometry that also had to fulfill all the other requirements to be a part of a loudspeaker, as well as being a waveguide. And we then got a much better result that is almost completely free from that kind of diffraction. So, in fact, this was for the blade. We wanted to get a mid-range diaphragm that was working as a rigid piston and had plenty of overlap, so the rigid piston band extended beyond the crossover point. And really, the first approach was to try doing some modal suppression. If this is a section of a diaphragm and it's the first mode, and you can see here the red curve, which is the deformed geometry, crosses the dotted curve, which is the undeformed geometry here. And this is a vibration node. So we know that if we drive it here, we won't excite the first mode. I mean, actually, these ribs, these LCP ribs, didn't just support the voice coil. We also moved the node to a more convenient position, and we raised the mode above the first mode much higher as well. So by manipulating the modes, we were able to extend the bandwidth quite a lot. I think the first resonance of this was about 9,000 hertz. We need an alternative method for this because using a 3-inch voice coil is not practical in a lot of the products in terms of cost. And also, the moving mass was quite high as well. So another technique was to attach the bottom of the voice coil former, the voice coil's up here, and this is the diaphragm down here, using a viscoelastic material. And by very carefully designing the material and the geometry, we were able to get a low mass and also a smooth response. So the red curve is the end result. The blue curve is what happens if you just glue the voice coil on. And this is really why people didn't want to use metal diaphragms, by the way. This was around the time that we moved away from polypropylene diaphragms where we were juggling with damping, with surround geometry, and accepting that there were going to be modes there and just trying to make them not too ugly. Through to saying, no, we want rigid piston behavior in the working band. That's really the only way of getting accurate sound quality. So just summarizing very quickly, you can get new things to happen if you use FEM correctly. And actually, we managed to get, at the end of the day, a driver that really quite closely approximates to our paradigm. So now I'll just look at enclosures. I'll look very quickly at the blade and then in more detail at the LS50. With the blade, the brief was to make the best possible loudspeaker. And the idea was to take this point source paradigm and to really try and push our technology. Now, this is kind of out of order of the driver work, because actually most of the driver work I've just shown was kicked off as a result of the Blade project. The owner of the company said he wanted the best possible loudspeaker and that we could have as much money as we wanted and we could have the best industrial designers and for us just to go away and have fun and do that. And actually we did just that. We spent, I think it was about 5 years between the start of the project and the end of the project, firstly making the concept blade, which was a couple of years, and then refining the technology and producing a production version that was manufacturable and actually improved the performance of the original concept. So, you know, a big part of this work has been actually being allowed by the company to go off and do things that might not be useful at all and that just might be interesting. And I've been very lucky that I've had a lot of support like that. So the driver array, which is the main thing I want to talk about, 4 bass drivers and the coincident source array here. And the idea was that because of symmetry, the apparent source of the bass drivers is just here. So it's on the same axis as the mid-range high-frequency driver away. And the added benefit is that because these drivers can be coupled mechanically and the magnet forces are opposing, we can cancel out the force from the magnet. And that instantly drops the vibration excitation down by around 30 to 35 dB, which is a massive improvement. The other thing I wanted to talk about was diffraction, and we were able to do some boundary element work on this. I mean, at the time, computers were quite a lot slower, and multi-core processing wasn't a thing of the day. So what I had to do was I actually had to do a quarter model. So in fact, I was just modeling, it was actually the bottom quarter of the enclosure, and I've just shown it mirrored to give an idea and a feel for what that would have looked like if we'd made it. And what we found we were able to do by having this waveguide geometry with the smooth curved outer surface, we could achieve very nice diffraction characteristics. So there were very few individual reflections. And you can see that from this curve here. This is the mid-high part of the real thing measured. And you can see that on axis we've got a flat response, and as you go off axis slightly, it gets a bit better. That's always the case. With these drivers, they've all got circular symmetry. So on axis is the worst place to listen to them. Slightly off axis is always better. And then progressively we lose more high frequency. So that really is very close to the paradigm, and it was good to be able to do that. So once again, wider dispersion and flat axial response sounds good. We made a lot of effort to really not add anything to the music at all. And at one stage I got a bit worried that this very idealistic idea of making a pure point source would end up with a rather analytic, dry and boring sound when it came to listening to music on them. But actually what we found was that because when you listen there's no distraction from other sources and reflections and resonance, that you just hear into the recording much more. And the ambience of the recording is really evident, the spaciousness is evident, the gaps between the notes of the musicians' performance are evident, and you get much more of an idea of how the music should be. So the music works really well. It doesn't actually need the loudspeaker designer to impose a flavor on the loudspeaker. It just needs us to try and let the music out. We also found that every single time we fixed a problem and simplified the behavior, we always got improvement in sound quality. We abandoned the KEF technique of using A-B switching and doing the odd ABX test. The reasons for that are quite interesting, and maybe this is a little contentious with some people, but my experience has been that A-B switching simply emphasizes spectral differences, and you can hear very clearly the tonal differences when you switch quickly, but your brain stops taking the music seriously, and you don't listen to music when you're doing A-B switching, you listen to spectral things. And really it's all about music. So probably the best example of that would be timing. Recently we've looked at filters that correct group delay. And if you do it really, really well, it has no impact on the spectral performance. You cannot hear it on an A-B test unless you train yourself specifically to listen for it. We tried doing just such a thing and listening to it, and we did A-B switching, and it was, there's no difference. Yes, but we worked really hard to stop the spectral difference, not surprising. Then we listened to a whole piece of music with the correction in, and then we switched it off, and it was instantly obvious that when we added the group delay back in, the musicians all sounded older and were playing differently. So the message is really, what we're trying to do with a loudspeaker is really about letting the performance get through to the audience and not getting in the way of that. So an unnatural thing like A-B switching isn't a good idea. It obscures subtle effects. And A-B switching is now not used anymore at KEF. I actually learnt about that at Tannoy. It was Alex Garner who taught me that. And it was a very useful bit of knowledge. So we'll move on to the LS50, which was an interesting project. KEF Marketing wanted a modern version of the LS35A to celebrate KEF's 50th anniversary. But the LS358, to put it mildly, is a legendary product amongst hi-fi enthusiasts. It's revered. People listen to it and pray to it. And really, it was obvious that the LS50 had to be absolutely outstanding. And for us to make something that wasn't outstanding would really be self-defeating. I know one engineer described the project to me as a poison chalice, because trying to do something to compete with a classic really is something that you should only take on if you've got really good reason to think you can do it, or if you're reckless, which is the category I fall into. So we started off in a classic way, and this is a good way to start a loudspeaker project. We did a lumped element analysis. It doesn't show any of the complex behavior, but it really clearly shows the basic behavior. So what we got from this model, and I'm not going to go through this in any detail, we modeled a reflex system, and what we get is we get output from the bass driver, which is the blue curve. The green curve is the output from the port, all looking lovely. And the red curve is the combined output. And we're able to adjust the alignment so that we get the right alignment. In this case, we picked a somewhat over-damped alignment because the LS35A was a closed box. And actually one of the biggest challenges was to make a reflex system that closed box lovers wouldn't absolutely hate. Because typically, people who like closed boxes hate reflex systems. They find them coloured. And actually, as we'll see, there's some justification for that. But the low frequency bit's kind of really well known. We know that if we put a gradual slope on it, it might not have quite such a good transient as a closed box, but you can get close. So then I started looking at some of the detail, and this was actually an initial prototype that was built by another engineer, and was really the point at which the owner of the company looked at the project and said, "There's nothing new, you're not doing it." And the marketing management then laid down the glove and they said to the engineers, "Look guys, you've got to come up with something really good. And we're not interested in doing something that's just average." But it was a very good starting point. It had a curious folded port here, which is a cylindrical tube and a box formed with 2 bits of wood on the cabinet that doubles the port length. A single brace linking the side walls. And for some of the later modelling, you'll see I've got a magnet here coupled to the front panel. The reasons for that will be apparent in a minute. But what we did with the model, the first thing is listening to it, the low frequency alignment did actually seem to work quite well. But there was some mid-range coloration. So I'll skip over the practical measurements, go straight to the FE. We did some modelling. Where the radiation was included, the diaphragm is moving with rigid body motion. And in particular, we looked at the enclosure radiation. And what we could see was that there was a mode at about 1,000 hertz where the cabinet was breathing. So the walls are going in and out. Now, the diaphragm displayed here is displaced at the same scale. Now, obviously, a real loudspeaker can't move that far, but I've exaggerated it so you can see the actual deformation of the enclosure. Now, you wouldn't have thought that that would be a problem because it's not moving much compared to the diaphragm, but the area of the enclosure is much bigger than the area of the diaphragm. So actually, in this particular case, the enclosure was radiating nearly as much sound. So we could see something on the response curve. We also noticed that there was some mid-range coming out of the reflex port. This just shows the first mode happening in the port. And we'd expect some sort of peaky output there. Actually measuring the prototype, because the FE models for this weren't that good because we didn't have the exact geometry. It was just a model that was lashed up. And it had some damping in it. But this was the actual thing. And you can see that there's a peak here, which was about where predicted. But some of the higher order modes couple into cavity resonances in the box. and they are louder than the main output from the bass. So expecting that not to be a problem is just not realistic. So time to start again. So the first thing was to have two planes of symmetry, to put the driver in the middle of the box. And straight away that gives an advantage in terms of the analysis. It means that the models solve much, much more quickly, and we can do more analysis more readily. But also, the implications of the symmetry planes have some impact further down the line, but I'll talk about that in a minute. So, taking another abstracted model, or two, what I did first was I looked at acoustic transmission from the sound coming from the rear of the diaphragm through the walls, and also the wall radiation due to the magnet vibration exciting the wall. So in other words, the walls act as a sounding board to the magnet vibration, which is the reaction from the force on the voice coil. This is the main signal, so that's the main output modeled. I haven't bothered with the reflex port. That is the vibration-induced radiation, and this is the acoustic transmission, which is pretty well negligible. So the first result really was, well, we can forget that. That doesn't matter. All we need to do is we just need to model the force of the driver, the force on the driver exciting the enclosure walls. But this is getting towards the main level. It's pretty loud, and it's at a frequency in the mid-range where the hearing is quite sensitive. So what I thought I'd do was I'd be clever, and I'd add some braces, and I'd actually add them to the plane of symmetry. Because on a plane of symmetry, I know that the structure, if it's all perfect, and certainly in FE land, the structure will just slide along the plane of symmetry. It can't separate from the plane of symmetry. So because it can only slide along, you can't get buckling on the brace, so it adds quite a bit of stiffness. And I managed to get just about an octave with these two braces, which is a pretty decent result. But really, when you look at it, all I've done is I've managed to shift it from several hundred hertz, where you can hear it a bit, up to 1.5 kilohertz, where it's really going to hurt. So not in itself a great result, but possibly a step in the right direction from the engineering point of view. So the next stage was to add some damping material between the brace and the walls. The benefit of that is it concentrates the shear forces in the damping material and allows you to absorb a lot of energy in it. So you can see the red material here is the damping, and it also is between the magnet and the brace as well. And the next stage was to optimize, firstly, materials. I was very lucky. I had a young engineer, Julia Davidson, who measured with the patience of an angel whatever materials I could find and threw at her. She measured gutter sealant, loads of different mastics, and eventually found something that we actually used in the factory as standard that had just the right properties to work well. And we could then just optimize the thickness and end up with a practical design. And this was the result we got. So the peak has gone. So that was a good result. And that actually set what became the target for secondary radiation being 30 dB lower than the main output. Now that was a slightly contentious target because some of my learned colleagues told me that we shouldn't be able to hear these things because of masking. But experience really tells me that it's safer to assume that you will hear it and to listen. And I think the difficulty is that psychoacoustic measures tend to be, the work's carried out under very specific conditions for a very specific purpose, and you can't just apply them willy-nilly. You know, with music, you listen more than once, you learn, and the whole thing's an adaptive process. So my experience is that assume you can hear it and listen for it and try and do some real testing. Don't try and work out what you should be able to hear, or you'll end up with an MP3. So this is just looking at the result I just showed you. This is an animation of both of the enclosures at their resonant frequencies. And I tried to scale them so the diaphragm motion is about the same in both models. I did as good a job as I could by eye. And you can see that there's a lot of movement here, and there really isn't very much there at all. I think it is moving 1 pixel if you look very closely, but it was quite a nice result. So looking at some real measurements for the cynics amongst you, we compared a budget chipboard enclosure, the LS35A and the LS50, with spot laser velocity measurements on the rear panel, just to get an idea and do a reality check. Is this stuff that looks great on the computer screen, does it really work at all? So this is what you get with a chipboard cabinet. You get some quite nice looking mountains here. Some really bad and really loud panel radiation that quite often will be just about as loud as the main part of the signal. The LS35A is very significantly better and is decently quieter than the main part of the signal. And of course the LS50 came out just as we'd expected, which was just as well, because by then the project was running very late and I'd have been in deep trouble otherwise. So that was quite a relief to see that. After that, I wanted to think about the air in the box. And what I wanted to do was to think about what would happen to cavity modes. Now, what I did was I modeled with FE the air in the box, and the green surfaces that show the approximate mode positions. And the danger is that if you put a driver here at the end of the box where the pressure variation at the antinode is very big, you'll end up with a dip in the response at the cavity mode. So somehow we want to avoid exciting these. So if we put the driver in our symmetric position here, we can straight away see that we're on one of the nodes and we'll avoid exciting that mode. And in fact, we'll avoid exciting all of those modes because all of them have a node in the right place so the driver doesn't excite them. And that's really cool because what it means is that when we optimize the stuffing, and I haven't shown that in this presentation, but I did a load of work, once again, using FE and optimize the stuffing position. And that caused a bit of consternation in the department because nobody believed it would really work. So I gave the biggest critic the job of going away with some bits of foam, and I said, okay, improve on it. And they came back 2 days later and went, I can't improve on it. It works. So this was an important step because it simplified the number of modes. It meant that the stuffing could actually be designed to work on just the few remaining modes. After that, we looked at the port design. Once again, we've got a longitudinal resonance. You can see more clearly in this simpler port. And what happens is the air pressure in the middle goes up and down, and you end up with a potentially big output here. And that output's in the mid-range. It's actually around 1,000 hertz again, so 1,000 hertz could be a bad frequency for us if we're not careful. So to control that, what I did was I added a flexible part around the port tube. So it's actually a bit of closed-cell foam wrapped around it. And the idea was that it would be stiff enough not to mess with the low frequencies, but would allow some of the mid-range frequencies to escape through the walls. And that did indeed happen, and it dropped the Q of the resonance and greatly reduced it. So we had to look after the diffraction side of things. The front baffle of the LS50 is a curious shape. That was designed using boundary element models where we'd look at the effect of the geometry, just a simple rigid radiating diaphragm again, and we'd display the results. So what I've done is I've taken phase and deformed the surface so it looks a bit like gravity waves in water, and shaded it to show the amplitude. So we'd look at this, and we'd also look at off-axis curves to try and pick the nicest geometry. So after all of that work and the work balancing it, for which I had a lot of help from the rest of the team at KEF, we ended up with something like this. So 0 degrees is black, 15 degrees is red, and so on. So reasonably nicely behaved for a simple not so expensive two-way system. And actually it's had a lot of very nice comments and nice reviews and plenty of awards. So I think that what we were aiming at probably was the right thing. So abstracted analysis really is key to this design. We got the secondary radiation down to minus 30 dB, and the high target of sound quality is worthwhile. I've mentioned the rest of it anyway. So, oh yeah, lots of small improvements can add up to a very big improvement. I think if you took one of these individual improvements out of context, I don't think it would actually make it into a good loudspeaker. You have to fix all of the things, and each time you have a problem that you can hear, it needs fixing. So now for something completely different. We're going to move off coincident source arrays and talk about coaxial drivers. There is a little bit of a link, but I have to warn you, it's all kind of backwards. So being backwards, we start off with a coaxial configuration actually made by a competitor. It's got a high frequency diaphragm here, which radiates through the throat, and a mid-range diaphragm here that also radiates through the throat. And the problem is the acoustic path is complicated. The HF might decide to go for a little wander up here, and the mid-range might wander down there. So there's a more complicated acoustic path. And I did look at some design schemes for this, but I thought it would be interesting just to look at another abstracted model just to show what's going on. So what I did was I took an annular outer diaphragm here, circular inner diaphragm. The annular one's the high frequency diaphragm, arbitrary choice. And I looked using rigid body motion once again of the diaphragms, but this time with a time-stepping finite element model, and we arranged the displacement to give a pressure impulse. So you can see the wavefront traveling here through the two ducts joining up to the single plane wave tube that I've modeled. And we've used a fourth order Linkwitz-Riley crossover between the HF and the MF. And you can see quite a few things happening. You can see, firstly, when we start again, you'll see diffraction as this wave diffracts very nicely. Then you get cross modes, and you've also got some longitudinal modes in here as well, which you can see, if you look at response curves, you can see those very clearly. You get some very big dips. So avoiding resonance with two drivers covering different bandwidths is very challenging. It's not an easy problem. The moment you end up with these ducts joining, unless you put the same pressure in both of them, you are going to have resonances. So that means these coaxial configurations for compression drivers are a bit problematic. So uncharacteristically, we decided to look at a single driver. And that was really a result of a comment made by Jack Ockley-Brown. He'd been doing a PhD on compression drivers and looking at the coupling between the structural modes in the diaphragm and the air in the cavity between the diaphragm and phase plug of a compression driver. And in the PhD, he'd come up with a number of quite useful things. He had a method of mapping to show how strongly the modes couple. And he also had some criterion that he thought would allow performance where the structural resonances wouldn't cause radiation from the device. And if you have a structural resonance that isn't radiating, then it's not really a bad thing. It's okay. And the criterion he came up with was to make the pressure and diaphragm velocity biorthogonal. So what that meant was that you end up with basically a sine and cosine, and if you integrate along here, you get 0. And so in terms of modal coupling, if you have these mode shapes, they won't couple. So you can put in the sine wave as an input, and you won't get the cosine excited. Now, to do this, we've got to change the paradigm of a diaphragm for a compression driver totally. We go from a rigid piston, it's very simple, the original paradigm, rigid body motion, just moves like this. 0 velocity here, fixed velocity here, like that, that's great. So we go from that to saying, well, it has to be clamped at the edge because we want to have a zero velocity here. And also, the diaphragm must flex. It's probably going to move something like this. It can work in the modal region as well. So this was quite a challenge for me as an old boy. Change everything that you thought, change all the rules you're used to working with and think in a different way. So a very interesting challenge. Just very quickly, looking at conventional diaphragms, they're intended to move as a rigid body. Normally they're axi-symmetric, driven with an axi-symmetric force. Most of the rigidity is from hoop stiffness that goes around the dome circumferentially. If you take an isolated segment like this of a dome, the resonance drops to 1/100th of the frequency. So almost all of the rigidity is from this hoop stiffness that's a consequence of it being axi-symmetric. And that's why those geometries are so loved by loudspeaker designers. So if we look a bit more deeply and we compare the two common compression driver diaphragm geometries and a biconical diaphragm, as I like to call this V-shaped thing, and a dome, if we give them both the same coil diameter and the same area, we can then compare them as diaphragms. And the first thing we notice, the red curve is the spherical diaphragm. This is the number of modes, and that's frequency. So the first mode for the dome happens here, but the other modes happen really quickly. So we're going to have to control an awful lot of modes with a spherical cap to get any increase in bandwidth. We're up to 20 here, and we get up to about 12K from 10K, from 9K. So that doesn't look very good. The biconic diaphragm, the increase in modes with increasing frequency is slower. And that's certainly better for the new approach. So the real issue is that the reason you have a coaxial design is because you can have a big mid-range diaphragm and a small HF diaphragm to cover a wide bandwidth. But if we want to do it with one drive unit, we've got to somehow get this big diaphragm area. And if we use an axi-symmetric geometry, actually we know that if we double the voice coil diameter, we will halve the resonant frequency of the mode. So we make it twice as big, but it goes up an octave lower. So that isn't going to work for us. So really, axi-symmetric diaphragms are really not going to help with this. So in a fit of insanity, I thought we should look at axiperiodic diaphragms. And actually, they're not completely unfamiliar, these geometries. And if you look at very old loudspeaker patents, you'll see lots of them, because they're kind of cool. But there are some good reasons why they can be very useful. So thinking about geometric stiffness, as with the hoop stiffness of an axi-symmetric model, we have planes of symmetry passing through the central axis here. And there won't be motion normal to the plane of symmetry. The material will slide on it. That adds some stiffness. And we'll have that, thank you very much. We need anything we can get, because we've lost all the axi-symmetric stiffness. And we can get rigidity from shaping the individual features on it as well. Now, this slide's a bit of a cheat, actually, because I hadn't worked this out when we, originally it was just, let's try those geometries, they're cool. Had no idea about this. But going back and thinking through it, this is a good explanation of why they're actually useful. So, this is a different finite element model of just half a segment of one of these axiperiodic geometries. It's got the same coil diameter, the same area as the previous examples if you look at the complete diaphragm. And what I've done is I've restrained the symmetry planes here on this edge and this edge, so the material will just slide along the symmetry plane, driven the yellow area, and clamped the ID and the OD. And what we get when we look at the increase in the number of modes is we can see that we've got a similar effect to the annular where the number of modes doesn't go up very fast. Actually, the first mode's at a decent frequency. It's reasonably high. But what's really interesting is there are actually two graphs here. what we did was we had one diaphragm that was double the diameter with double the cyclic order, in other words, double the number of features around it. So we didn't change the feature size, we just had more of them around the diaphragm. And perhaps not surprisingly, that has almost no effect on the resonant frequencies. So we can go from a 2.5-inch coil to a 5-inch coil, and we can actually expect it to work very well. So in terms of being able to make a big diaphragm, this actually looks very hopeful. And of course, it's clamped at the ID and the OD as well, which is another thing that makes it quite hopeful. So this is just an example. I don't have time to go through coupling maps of things that don't work. So a really bad one would all just be bright red. These are the acoustical modes here. So that's the 0th mode and the 0th mechanical mode, just the flexing. This bit here you want, this gives the main radiation. So it's set to 0 dB. And the idea is you look at the relevant bandwidth and you pick the relevant acoustic modes and you look at the bandwidth of the mechanical modes, 20K is about here and here. And you try and get the colour on the coupling map to all be blue. So none of the modes couple. And if you do that, then in principle they shouldn't radiate, if you make the thing perfectly well. Of course, there's going to be a limit to just how many, there's going to be a limit because the modal shape of the real thing won't be exactly the same as the model. And manufacturing errors such as the stretch in the material and work stiffening, all sorts of things will affect the actual modal shapes. So in the real world, we're not really going to manage to correct 10, 12 or so modes. Maybe 4, maybe 5, that kind of number in the real world. But this is what half a segment looked like when Jack had actually optimized the geometry using his technique, using that coupling map and other criterion. We actually considered the linearity, so the KX linearity with motion we considered as well. Fundamental resonance we considered. And we ended up with a diaphragm that was 125mm voice coil. That was no accident, that's what we defined it to be. We found a width of 36mm wide was really the biggest width that we could make work for the bandwidth that we wanted. And this is for a large compression driver, so really up to 12,000 hertz is the important region because you wouldn't use a system with these drive units in a room this small. I think the people at the back would be the nearest you'd want to listen to one of these things at. This is what the whole diaphragm looks like. It flexes, so when the voice coil drives here, the motion is like this. It's got a lot of fine detail on. The distance across here is less than 19mm. So the detail on it is as fine as a small tweeter. And perhaps because of that, we found it was stable, forming it in 30 microns. We'd actually anticipated and thought we were going to be clever to get away with 50 microns, which is the normal 3-inch diaphragm size. And considering this is 6.5 inches across, 50 microns seemed like a fairly ambitious target. But when we actually formed the diaphragms and picked them up, the 50 micron was ridiculously stiff. And the 30 micron just was right. So it's like the 3 bears, the porridge was just right, and we had to have it. That was really good because it gave us an unexpected mass advantage, which got us below the mass of a normal diaphragm per unit area. The fundamental resonance was low. The original version of this had a big air cavity, and the resonance was actually down at 100 hertz. We changed that because it was crazy low and big. And the first breakup mode was about 9 kilohertz. Now, considering we can move the same volume of air as a 5.25-inch conventional compression driver, which would break up around probably 6K, 5K, the breakup was actually beating a conventional dome of that size. And as I mentioned, the compliance linearity is very good as well. So for the acoustic design, we used some techniques that were developed at Keff and Celestian for designing the position and the size of the air channels. It's the extended Smith method. And if anybody wants to know more about that, Jack Oakley-Brown has done a lot of work on this, and he's here. So bar-time conversations about the mathematics of phaseplug channels could happen. They could, if anyone's brave enough. So, in fact, sorry, let's just go back a sec. So what we do with these models, the way we compare them, is we terminate this with rho C, so it's like an infinite tube, because it's too small to get cross modes. And we then look at these three pressures. And in a perfect drive unit, the three pressures would be the same from DC up to daylight. What we get with this drive unit is actually very nice. It's a shame I don't have time to show normal ones because they're far worse. And we've managed to make it work up to about 9,000 hertz really well. And these deviations here are actually quite small compared to a normal compression driver. The normal ones would be, they'd be huge, be really big variations. So there are no large resonances. Now, to put that in context, we've got Ka equals 10, and that's, the low frequency is a bit arbitrary because you could use it lower, but that's probably sensible in terms of working frequencies. Ka equals 10 is about double the bandwidth that you get on a normal compression driver. So just to finish it off, you have to join up the air channels to the throat, and that's just a simple matter of making sure that the flare, the area down these tubes, expands correctly and the path lengths are right so that the waves sum nicely at the exit of the phase plug. I've just shown 10 kilohertz here to show it can be done. But actually at most frequencies this looks like that, and it works really nicely. So just very quickly, a plane wave tube result, that's the fundamental. Above 8 kilohertz, because it's a 2-inch tube, there are cross modes, so you can't trust it. But what I really wanted to show with it was the low resonance, so we made the driver much smaller. It went from being that big down to being about this big. And the distortion down at low frequencies is really low. And we did try it on a test horn. We found we could get about 15 dB more SPL for 10% harmonic distortion at low frequencies. I think it was 200 hertz that we did that at. So we had a lot more output than the benchmark drive unit. So that's what the final driver looks like. You can just see where the diaphragm lives down here. It's a pot magnet. The poles have to be shaped to give enough air volume, and the air volume goes up inside here as well. And I've got one of those devices. I can pass that round. That's actually the phase plug. I'm sorry I haven't got a diaphragm. They're a bit scarce at the moment. We keep on breaking them, and we're doing power testing to get it in production. So the new thing I learnt here, really from Jack, was that the analytic approach is vital to actually understanding what you might be able to do and to get there as well. So just FE on its own doesn't really get you the whole distance. Although it's a very useful tool, you need to also use analytic techniques as well to make real progress. So just to conclude, I'm done now. So abstracted models allow you to isolate phenomena. Virtual prototypes give a complete view of the behavior. The FEM, together these things really allow a step change in performance. You can make big improvements in performance. Subjective evaluation is really vital. You can't leave it out. Whatever anybody says, we're quite good at the engineering, but it would be crazy not to do the final balance by ear. And also psychoacoustics, it can be applied to loudspeakers, but be really cautious when you do it if you know as little as I do. I'm sure there will be progress made on that, but at the moment, my experience of psychoacoustics is that although Floyd's criterion works very well, I wouldn't rely on masking theory to tell you what you can and can't hear. So thank you very much. I'd like to I've got some thanks to go particularly to Jack Oakley-Brown, who really showed me the pleasure of working with a really talented team. And between us, we've built up a fabulous team at KEF. And there's a great deal of teamwork. So also thanks to the teams at KEF and Celestion, because without their support, none of this work could have been carried out. And of course, the owners, and Keith and the IOA for inviting me here. Thank you very much.